Good morning. This is the companion video for the MCTC Principles of Chemistry 2 Determination of an Equilibrium Constant lab. In this lab, you will have collected volume information and spectroscopic data, percent transmissions, and you'll be asked to use this information to determine an equilibrium constant for a chemical reaction. Several different trials are performed, also at different temperatures, and this Excel data sheet, or Excel spreadsheet, is something that you'll find on the course website and is meant to help you perform these calculations using a spreadsheet more quickly and more accurately. It is possible to perform these calculations with a calculator, but it will take you quite a while. It's much simpler and quicker to do it with a spreadsheet. So the bulk of what you're looking at right now is the spreadsheet that is furnished. However, we need some data, and I'll scroll off here to the right to show you what I have. In the box is the handwritten data from a particular student's experiment. What I've also done is I've transferred that information to the spreadsheet by typing in to all of these cells the values that belong there. So these two tables, the first for iron nitrate and the second for KSCN, have initial and final burette readings. Now, the actual volume of either solution that's been dispensed is the difference between these two. And so rather than do this on a calculator, I do need to know how much of the iron nitrate solution was dispensed. Okay? Rather than do this on a calculator, which would be trivial, I'm going to create an equation to do this, beginning with an equal sign, and I would like to subtract 1.19 minus 0.07. Okay, having entered an equal sign and the coordinates of those two cells, I can hit enter and I get the net volume measurement that easily. Better still, I can take and copy that equation into all subsequent cells in order to determine the net volume added for all 6 trials. Next, we have to do the very same thing for the KSCN. Again, the equation begins with an equal sign, and we would like to subtract from 9.05 the value 0, which is trivial again, but having written that equation, I can click and drag it, and now I have all of the net volumes for all 6 trials that easily. These net volumes do make an appearance in the spreadsheet, and they are located right here. Now, the volumes that are listed in the spreadsheet are volumes that are prescribed by the lab handout. If you were doing the experiment and working hard to deliver exactly with 2.0 accuracy, these volumes, you wouldn't need to do what I've just done. But for this experiment, we didn't dispense 1 milliliter, we dispensed 1.12 or something like that. So I'm going to go ahead and just delete all of these values because I need to replace them with the values that I've just calculated. Let me scroll off to the side and grab the first set of net volumes. This is for the iron. Highlight, right-click, copy. Back over here in the upper left-hand cell, right-click, and from the paste options, choose Paste the Values. So there are all of the volumes that we determined for the iron solution. I can do the very same thing for the SCN. Coming over here for the SCN solution net volumes, right-click, copy. Over here, right-click, paste the values, and we're good. Okay, so the other thing that was done in this experiment is that solutions 1, 3, and 5 were also tested at a lower temperature. And so their volumes are in fact the very same as those for the warm trials. And so I'm going to copy and paste for vial 1, copy and paste for vial 3, copy and paste for vial 5. And that's all there is to that. Okay, so I have in the spreadsheet now all of the volumes that I need to determine the initial concentrations of these different ions, and we'll do that in just a second. But let's go ahead and just follow the spreadsheet from left to right. The next column asks for our transmission values, and the transmission values that I have are in this table right here, and they can be entered just as you see them as numbers. Okay, we are not going to enter any sort of percent notation. I'm just going to enter the first number for trial 1. Notice it is not 100.24. The first entry is actually 71.93. It'll get converted into scientific notation. Don't worry about that. It's still there. It's still represented properly. The next one, 59.01. 46.46, 46.72, scrolling down a little bit. What have we got next? 50.6, 61.74, and then we're into the cold trials. Okay, and the cold trials here in the second column, for vial number 1, the cold trial was 65.36. And for vial 3 was 41.47, and for vial 5 was 43.72. And then last but not least, there is vial 7, which is a room temperature trial, and at the very bottom of my handwritten table there, you'll see that that is 24.32. Now, just taking a quick glance back to make sure that everything was entered properly and that I didn't reverse any digits or make any other mistakes. Things are looking pretty good. 61.74, 65.36, 743. Good. Everything's been entered properly. Okay. So the next thing that we do is we calculate absorbance. Now, absorbance is calculated very easily by just taking the negative base 10 logarithm of the percent transmittance divided by 100. So this is the equation that we can apply to our transmission values to calculate absorbances. We're going to do that with an equation as well. So I'm going to go to the first of these, trial 1, absorbance, and the equation, as always, begins with an equal sign, then needs to have a negative log, that'll be the negative log, and then we want to take the negative log, parenthesis, of this value here in F13, end it with a parenthesis, whoop, that's not quite right, and divide by 100, and then end it with a parenthesis. There we go. I forgot about the divide by 100 piece. If I hit enter, I get a value of the absorbance. And in this case, the absorbance is 0.1431. That's 1.431 times 10 to the minus first power. That equation is working properly. I can grab this little handle and copy it all the way down. I now have all of the absorbances for all of the percent transmission values. Very good. We're well on our way to completing this spreadsheet. Now, here's something quite important. As we move into the I, which stands for initial, remember that these initial concentrations when performing equilibrium calculations almost always, not always, but frequently, require dilution. And so these concentrations that we have here for the iron, the FCN, and the product ion, FeSCN, all require dilution calculations based upon the volumes of the solution that we have to work with. Now, keep in mind that the concentration of the iron ion was given to be 0.00200 molar, and the concentration of the FCN solution, I'm eliminating or not acknowledging spectators, is the same concentration. So we know their concentrations, and from the spreadsheet we have their volumes. So how does one go about doing this? Well, the final concentration, M2, will be equal to M1 V1 divided by the total volume, and that's important, okay? This is just a reformulation of M1V1 equals M2V2. The idea being we need to calculate the concentration. M2 is our unknown, but M1 we know is going to be 0.002. The volume 1 will be whatever volume we get from the spreadsheet for either the iron or the SCN, and then the V total will be the combined volumes of the two that were put together, the Fe and the SCN. So let's see how that looks like, what that looks like as an equation. Okay, so as an equation, I'm going to punch in an equals, and then I'm going to go ahead and utilize parentheses just to do the best job that I can at compartmentalizing and organizing the calculation. These parentheses can be utilized in different ways, but I'm going to begin with a parenthesis. The idea being here, I need to take M1 and multiply it by V1. Well, M1 is 0.002, so I can enter that. That's easy enough. Times is the asterisk, and V1, this is the iron now, we're in the iron column. V1 is found in cell D13. So D13, and you'll notice off to the left, I've highlighted the volume of iron that I have used in this particular trial. I'll close the parentheses, and that completes the top part, the M1V1 part. Now I need to divide by, and I'm going to do this in parentheses again, I need to take the total volume and put it in the denominator. Now the total volume is made up of both the iron solution and the SCN. So that will be D13 plus E13. End with the parentheses to wrap things up and hit enter. And you have the initial concentration of iron ions just that easily. All right. Well, having gotten that equation right once, I can get it right a whole bunch of times. And so there are the initial concentrations for all 6 trials. Okay. Next up, the initial concentration for SCN. A very similar recipe here. I'll go through it one more time. Equals, I'll stick with my use of parentheses, the initial concentration M1, 0.002, times, and then we need to multiply by V1, which is this 9.05 over here in cell E13. That's another way of selecting it. You'll see it filled in automatically. Hit a parentheses, then divide by, and now, again, the total volume. So we want what is in D13 added to what is in E13. Okay, that's the total volume, both pieces combined. Hit and enter, and now I've got the initial concentration for the SCN. Click and drag it down, or copy and paste would work as well. And we have the initial concentrations for both of the reactant species, iron and thiocyanate. Now, initially, moving on to the product, initially there isn't any product, and so we can go ahead and populate all of these cells with zeros because there just isn't any of that stuff yet. Of course, that's going to change once we let this equilibrium loose. Okay, so up to this point, we have done the equilibrium problem, and we've done the initial stages where we calculate concentrations. Let's keep things moving along. We have this next column, which is the change. Now, FeSCN in this case is going to be equivalent to X, as you can see right there. And the idea is that we do this spectroscopically. To be able to calculate the change in this case, we need to generate a calibration curve. Now, the calibration graph or curve, instructions are right down here. You are to use your absorbance for the for vial number 7 and only vial number 7, and type it in right here. So that's 6.14 E, that's times 10 to the negative 1. That goes into that cell right there. The concentration for vial number 7 is also known to be 2 times 10 to the minus 4th molar. So now we know what now we have both the point 0,0 and the point 6.14 times 10 to the minus first and 2 times 10 to the minus 4th to graph. We have 2 known absorbances and 2 known concentrations. It's necessary to double up on the zeros. It's a trick to get Excel to deal with the graph in the way that we want. But we do create the graph by highlighting all cells, inserting, look for scatter plot, click on scatter plot, and go ahead and connect the lines, and that will be the graph. So again, the way that was done was we highlighted all of the data in that table and we created a graph from it. And here we have the calibration curve. Now, this is a piece that needs to be included with your report. I am not going to bother labeling the axes titles or title the graph per se. I'm more interested in moving on with the calculations, but you should make your graph presentable before you put it into your lab report. The next thing that we need to do with the graph, though, is we need to add a trend line and display the equation on the graph, which is what I have right there. Now, that isn't much of an equation, of course. It's only 2 points, and you get a perfect straight line. I'm going to format the trend line label, go to the Number tab, and crank up the number of decimal places to something ridiculous like 8. And we can see that that 0.0003 has more behind the scenes. It's actually 0.00032573. What does this mean? Well, in this graph, let's increase the font a little bit just to talk about it. In this graph, X isn't really X, it's absorbance. And Y, we have to get this over to the side a little bit, and Y isn't really Y, it's the concentration of the FeSCN plus 2. Okay, it's the product ion concentration. So this equation is what lets us convert absorbance into product ion concentration, which, gang, is the same thing as X. So this little equation here, which is a very straightforward multiplication, can be applied to all of our absorbance measurements to determine the actual concentration of the product ion, the orangeness, if you would prefer. So coming up here to the table and trying to keep all of this on screen at the same time, we're going to calculate this product ion concentration using the equation that you see at the bottom of your screen. It is going to begin with an equals, okay? And we're going to go 0.0003 2573. 2573, good. And we're going to multiply that, asterisk, by the absorbance over here. Click. And then hit enter. There you have the concentration of the product ion for vial number 1. The equation, being correct, can be then copied and pasted into the remaining cells, utilizing the very same trend line application. We have now determined the change that takes place for all of these solutions. Okay, so we've got in our ice problem, we have the initial concentrations that required dilution. We have the change that required a trend line equation to convert absorbance into concentration units. And now we move on to the equilibrium level. So this is an ICE problem. And a little hint to you right up here, initial minus X is going to be the equilibrium concentration of the iron ions. Remember, iron ions are a reactant and their levels need to go down. So how does that work? Well, I need a little bit more space. Let's get it all on screen here. Okay, so the initial concentration of the iron is this value right here. the X value is this value right here. So what I need to do is I need to subtract those two. Go to the cell, hit equals. Then I want to take the initial value, click, minus the change, click, and hit enter. And there is the equilibrium concentration of iron ions. The calculation's correct. I can copy it all the way down. Oop, one more. There we go. Now we have to do the same thing with the SCN. Now the initial SCN is right here, and the change is right here, and it's a subtraction. So I will begin this equation with an equals, and I'll take the initial concentration, which is in cell I13, and I will subtract that from the change that takes place, which is in K13, and hit and enter. All right, the equation seems to be working. Paste it into all of the subsequent cells. We've been working on the reactant side, and in this case, reactants were consumed, but products were produced. That is demonstrated by the use of the plus sign right up there. Let's see if I can't. Right there. So for the equilibrium level of the product, what we need to do is take the initial concentration of the product ion concentration, okay, which is 0, and we need to add it to the change, which is the same change as we've been having here before. Now you've noticed that the initial concentration is 0 in all cases, and so there's really no point to including that in the calculation. Rather, it's perfectly fine if we just let this cell equal the contents of the change. And if you want, you can add 0 to it, but it doesn't really matter. It's really just that number because the initial levels were 0. And there we go. So now we have all of the equilibrium levels. Just a reminder as we come down now, the home stretch, recall that the equilibrium constant is equal to the product ion concentration, which we now have in equilibrium conditions, divided by the equilibrium iron level, divided by the equilibrium SCN level. So we need to take the product amount and divide by both of the reactants. In this cell right here, in the Kc, or equilibrium constant column, what we'll do is, again, write an equation, equals. Now I need to take and I need to divide oops, that's not quite where I wanted it. Never mind, we need to be right there. Okay, we have an equal sign to start out the calculation, and then we need to take the product ion concentration, which is in cell N13. Okay, that's the product. And we divide that by, I'll use parentheses just to make things very clear, divided by the product of the iron concentration at equilibrium times the SCN concentration at equilibrium, and the parentheses and equals. And there, gang, is the equilibrium constant from the very first trial. It's in about the right range. These do vary somewhat, depending upon temperature, ambient lab conditions, and solution preparation, but that's a very reasonable equilibrium constant. And better yet, after having done that, I can copy and drag and bring that equation down to see what the equilibrium constants are for the remaining trials. As you can see, the constants are somewhat constant, and I'll leave it up to you and your lab report to interpret these results and write up your analysis in that lab report. That's it. Any questions, let me know.